Welcome back to Calculus 2, Section 2.4, Arc Length and Surface Area. We have two topics to go over, arc length and surface area. We're going to begin with arc length, and the arguments that we do in arc length can be carried over to produce surface area. To get started, let's look at a red curve. Consider starting at a point on the red curve, following the red curve until we get to some ending point. The distance traveled along the curve, we term that the arc length. If we look at the beginning point, the ending point, we can easily use the distance formula to find the distance between those 2 points. And then if we find successive intermediate points, we can again apply the distance formula to find the length of each of these line segments, add up the lengths of the line segments, and get an approximation to the arc length. The more line segments we use, the better the approximation becomes. All right, so take a curve, start at a point, end at another point, and pick some intermediate points. Now, pick an arbitrary ith line segment. If this is the ith line segment, let the point off to the right have x-coordinate xi, the point off to the left have x-coordinate x sub I minus 1. Good. Introduce notation. We'll let the line segment have length s sub I, lowercase s. And we know that adding up all of these s sub i's will give an approximation to the arc length we desire to calculate. All right, so let's think of a way to express out a formula for computing s sub I. So we can draw in a right triangle where s sub I is the hypotenuse. Label the sides. Remember, our convention is to always use a regular partition so that the base will always be delta x, and then the height, delta y, is the change in the y-coordinates. State the Pythagorean theorem. And then do a little bit of algebra. We have two terms as a radicand. Factor off the delta x. There are two copies of the delta x. If we factor that off of the first term, we're left with a 1. To factor it off from the second term, we need to divide the second term by delta x. Having it factored off, we can write it out as its separate factor. As delta x is a positive term, we can apply the radical and recover just a delta x. And in the first radical, we can use the mean value theorem. Since delta y sub I over delta x, that's just the slope of the secant line going through these 2 points. Mean value theorem says that there is a point somewhere between x sub I minus 1 and x sub I, such that the tangent at that point to the curve equals the slope of the secant line. Beautiful. We're all ready to go. We have as our integrand this radical term. The delta x is going to become the differential dx by taking a limit in the number of partitions. Here's a formal statement of what we've just gone over. Let's start with a hypothesis. That we need to assume that f is a continuous function, but also that it's differentiable. And let's look at the integrand to see that the integrand is a radical. Radicand's a sum of a constant plus something squared. And the quantity that we're squaring is the derivative of f. So in order for this quantity to exist, the function needs to be differentiable. All right. So the arc length, which we'll term lowercase s, is given by this definite integral. And it's the length of the curve from this beginning point, a comma f of a, to this ending point, b comma f of b. Very good. Now, for this example, let's go back and look at the formula. For this example, we're going to take x to the 3/2 as our function. Let's go back to the formula. The formula involves a radical, and often it's difficult. We have to work hard to find an f such that plugging into this formula will lead to an elementary integral. But x to the 3/2 is one such function. Let's look at the starting point, the origin, ending point 1, 1. All right. Let's set up our integrand. We're going to need the derivative of the function. X to the 3/2, 3/2 comes down, decrement the power. Here's y prime. We're also going to need y prime quantity squared. We're also going to have to add 1 to that expression. 3/2 goes to 9/4. X to the 1/2 goes to x. We're going to want to apply the radical to this expression. So let's combine these two terms into a single term. Good. Set up the integral. When we apply the radical, we know the radical of 4 is 2. That's just a constant. And then we have a simple integrand, which can easily be evaluated thanks to a change of variables. So if we make the change of variables, u equals 4 plus 9x, the differential du will be 9 times the differential dx. Make an adjustment by introducing a 1/9. We'll have to change our bounds. 0 to 1 are the bounds for x. Plugging in x equals 0 gives a lower bound of 4 on u. Plugging in x equals 1 gives an upper bound of 13 for u. Nice, and then evaluating out, we come up with our answer. So again, have to work kind of hard to cook up an example where it works through. Here's one for you. X to the 2/3 is the curve beginning at 1, 1 out to 8, 4. What is the distance you travel if you follow the curve? Alrighty. Now, in contrast, something like sine over half of a period following the sine wave, what is the distance you would travel? When you set up the arc length integral, well, the radicand 1 plus cosine squared, you're kind of stuck. So what do? You go to a computer, go to a calculator, and you plug it in. Now, what we're getting is we're not getting an exact value. The calculator is returning back. It's printing out an equal sign. Taken from a mathematical perspective, this is incorrect. This is only an approximation. From an engineering perspective, this is perfectly fine. As long as we appreciate that this decimal expansion or decimal value is only an approximation of this definite integral, there's no problem. What's happened is we've used software, we've used techniques of numerical integration, something we'll get to later in the videos, to evaluate the definite integral. But this is not an exact value. Okay, here are some examples for you to try. Same domain, but change out the function, and then come up with an approximation. Very nice. That's arc length. Let's move on to surface area. And let's take a look. All right. So here we're looking at what might be a portion of a rocket engine. We have a bounding box where there are x coordinates going from 1 to 4, y coordinates going from -2 up to 2, horizontal x, vertical y, and then depth-wise a third variable z. Letting z be 0, we can come up with the xy plane. In that xy plane, we have the x-axis given here in orange. And then on the y-axis, vertically, in this xy plane, we've sketched out in blue the radical function y equal radical x. The shell, shaded in orange, is the revolution of y equal radical x about the x-axis. We have ghosted circles in gray, representing points along the curve at which we determine a radius and then revolve about the x-axis. Let's take the case of x equals 4 and x equals 1, if we take x equal 1, and revolve about the x-axis, produce that circle there. All right, so we've already gone over arguments for how to compute the arc length of the curve. What we want to do is we want to come up with the surface area for this shell. Remember, back in computing the arc length, we considered points along the curve, found the distance between the 2 points, added those up as an approximation, passed to the limit. Okay, our technique here is going to be similar. We're going to take points along the curve, and let's take these 2 points, that those 2 points lie a distance from each other, and we want to revolve them about the x-axis. In doing so, we produce this object called a frustum. What is a frustum? A frustum is a portion of a cone. So here would be the bottom portion, and then this top portion has been lopped off. And then what remains is called a frustum. So we want to consider the frustum, but in order to analyze it, we're going to need to consider the entire cone that it comes from. So let the cone have height h and radius r. You should see a right triangle here. Hypotenuse L, that will be the lateral length. And we're going to need a formula that the lateral surface area of a cone is given by the formula pi r L. Good. Let's put that to the side. And then give ourselves a little more working space here in the frustum, make it a little larger. Now we have dashed in the upper portion of the curve that we are lopping off. And we've introduced notation R1 and R2 for the radius of the smaller circle at the top of the frustum, and R2 for the larger circle at the base of the frustum. We'll also need to introduce S as the lateral measurement of the frustum. And now let's relate these four values through similar triangles. So L is a hypotenuse for a large right triangle with base R2. L and R2 at the bottom. And then we have a small right triangle with this hypotenuse and base R1. So base R1. And hypotenuse, well, that's the lateral length of the overall cone. Subtract away the lateral length of the frustum, L minus S. Good. Time for some algebra. Let's begin by cross-multiplying. Clear out the denominator. R1L, R2, binomial. Distribute out the R2 on the right-hand side. And then collect on the right terms involving L, and collect on the left the R2S term. And then on the right, factor off the L. Good. Let's go ahead and solve for L. Divide through by this coefficient, R2 minus R1. And then save this expression for L off to the side. Now, we are interested in coming up with the lateral surface area of the frustum, and we can use the familiar big minus small. Thanks to the fact that we have a formula for the lateral surface area of a cone, and the frustum is the overall large cone, and then take away the top portion of the cone, leaving just the bottom portion, or the frustum. So big minus small. Let's plug that in to this formula, pi r L. For the big cone, the overall cone, pi r becomes pi r2, and then L is L. For the small cone, that's the portion that we are removing, the top cone, pi r is pi r1, and then for L, we want this measurement, which is the overall lateral measurement minus the lateral measurement for the frustum, L minus L. Excuse me, L minus S. All right. Play around with this. We have a difference of two terms. Each term has pi. We can factor off the pi and then distribute R1 onto the binomial. And then inside these three terms, we can collect the terms involving L, factor off the L. It then has a coefficient of R2 minus R1. And now let's plug in for L. Here we have L. Plug in for L. Get a nice cancellation. Clean that up. And then we have that the lateral surface area for the frustum is given by this expression, pi times this sum. The sum has a common term, common factor, S. Factor it off. And then if you factor that off, then you're left with R2 plus R1. But if you take R2 plus R1, divide by 2, that would be the average value of R1 and R2. Let's term that r star. So if we want to write out r star, well, we're dividing r1 plus r2 by 2, so introduce a 2 in the numerator. And note that what we have is 2 pi r, which is a circumference of a circle, and the r that we're using is r star, the average value of the r1 and r2. And then you're multiplying that by s to come up with the surface area of this frustum. Beautiful. Okay, let's go back to the original picture. Now, we want to know this r star value, and that r star value is occurring along the curve y equal f of x. So let's swap out r star for f at x star. And then this is just for one frustum, but we know that there are many, many frustums, n frustums. So for the ith frustum, what is its surface area? Well, let's denote that with SA sub I. And then copy over the formula that we just had down. And then update the length with S sub I. That's the length of the portion of the curve between x sub I minus 1 and x sub I. And now we can go back and we can recall from the first part of the video that we have an expression for that arc length, thanks to the Pythagorean theorem and the mean value theorem, that S sub I is expressed as this radical product delta x. Very nice. So now we do the familiar, add up these component values to get an approximation for the overall value. And then looking at that sum, we can notice that we have a Riemann sum. And hence we wish to pass to the limit as n goes out to infinity. Note that we're using an xi star as well as an xi double star. And you want to think, well, okay, each of these, though they're different, they're each coming from the ith subinterval, so that as n is taking out to infinity, do you see that each of these xi star and xi double star will both limit to a same x. Okay, taking the limit of the Riemann sum, we can rewrite this out. Our surface area has this formula. Take a look, it's 2 pi r, r gets swapped out with f of x, times a distance. Very good. Let's go ahead and apply this formula for this particular picture. Our bounds of integration, a to b, are 1 to 4. Our function f is the radical of x. And then taking a derivative of radical x, 1 over 2 rad x, quantity square that, and then combine these two radical terms. Do a change of variables. Now an elementary integral, and evaluate out. Very nice. Okay, so the surface area of this object is here. And then this object, if we manipulate it, if we rotate it, it's still the same object, so its surface area is going to remain the same. So that if instead of its original orientation we have this orientation, we should look for the curve given out as a graph x equals g of y from some input y equals c to input y equal d, and revolved about not the x-axis, but the y-axis. And then the formula would be updated as such. And let's try an example here. So this lampshade is produced by rotating y equal 1 over x, not about the x-axis, but about the y-axis. And then with inputs coming from y equal 1 to y equal 2. All right. Let's set this up. If we apply the formula, we're going to want to rewrite out y equal 1 over x as a function of y. Now this is only a nominal change of having input be x to input be y. It still has the same form. In your example that you're going to do, you want to make sure to explicitly compute out the g. Okay, and then plugging into the formula. So g of y is 1 over y, g prime is negative 1 over y squared. And then looking at this, we need some assistance in computing out a value. So we appeal to a computer program and come up with an approximate value. So the main thing here is the setup of the integral. So you give it a try. Now, we have the base of a lamp pictured. We have that this blue curve is expressed out as y given as a function of x, but we're not rotating about the horizontal axis, we're rotating about the vertical axis. And thus you're going to need to solve this equation for x. That's going to require completing the square. Also note that you're going to need to rephrase these values of x into corresponding values of y in order to come up with the bounds of integration. Okay, so a little bit of detail to take care of in this assignment, but you should have fun. Very good. That brings us to the end of this video. Please like if you find this useful, and thank you for watching. See you on the next one.